Hello students, welcome back. So for lesson 10, we had been studying only the theoretical aspects of factor groups. First, the definition, and then the construction of the group structure, and finally the fundamental homomorphism theorem, along with all the proofs. Now finally, let's consider an example. Here's an example provided by our textbook author, and frankly, I'm not so sure whether this is the best example we can consider now, but here it is anyway, according to our textbook author. Let's determine this factor group. In other words, let's re-express this factor group in terms of a simpler group, which is essentially the same, or isomorphic to this. Let's take one step at a time. Let's simplify just a little bit by simplifying this expression here, because everything else here is written in terms of the residue class Zm, except this one red. So is there any good way to rewrite this trivial subgroup into a residue class group, Zm? How do I do that? In other words, rewrite this thing here, highlighted in red, as some Zm. Suggestion? What is this question mark? It is Z1. Why is that? Well, this has one element, 1. Z2 has two elements, 0 and 1. Z4 has 4 elements, 0, 1, 2, and 3. In general, Zm has m elements, 0 to m minus 1. Likewise, Z1 has 1 element, 0. 1 minus 1 is 0. Another way to look at the same thing, divide any integer by 1, then the remainder is 0. In any case, we got it. And then one more simplification. This Z2 in the numerator and this Z2 in the denominator, we can cross those out, simplify those, and what do you get? We get this over this. And then what is 4 over 1? 4 divided by 1. Yep, we have Z4. Does it make sense? Basically, this is what we did. This trivial subgroup is rewritten as Z1. And then we took off this Z2 and that Z2. One is in numerator and one is in denominator, so cross those out. And then what's left is Z4 over Z1. What is 4 divided by 1? 4 over 1 is just 4, as we have here as the final answer. Does it make sense? Yes, it does, of course, but the problem is, how do you prove it? Well, we're going to prove a little bit more general case in section 6, but for now, let's look at it in terms of 5.3, the fundamental homomorphism theorem. Let phi be a group homomorphism from G to G prime, but G prime is too big because we are focusing upon the image phi of G, which I'm highlighting in purple right now. So let's consider phi as a homomorphism mapping from G to its image phi of G, which is a subgroup of G prime. And then this one here, purple, and this one here, blue. And if you look at it in terms of blue to purple only, then it's an apimorphism. Homomorphism, but onto the image. So if you have an apimorphism, then this is what you get. The domain over the kernel is image. So domain over kernel is image. That's a canonical isomorphism. Domain over kernel is isomorphic to the image. Now let's look at here. And this is a domain. So we want to find out a certain map from Z4 times Z2 to Z4. You see, G prime is too big, and considering some G prime much bigger than Z4, that's unrealistic and useless because we are going to consider only up to phi of G, the image only. So let's just consider an epimorphism. So that's the image. Oh, let me rewrite it like this. So that'll go to phi of this, the image, and that's just equal to Z4. Okay, all right. So that's just the image. We have an epimorphism, all right. And then this is a domain. So the image, purple, is domain blue over kernel K. What is kernel in this case? Well, in order to have kernel, we have to find out what phi is. So we have to get phi. Any idea? So that the kernel is this one here. I have to have a bar here because we are dealing with residue classes. Basically, this is what we want. With all the color coding. So, domain, image, kernel. So that the image is isomorphic to domain over kernel. The domain why am I doing that? I'll have to rewrite everything here. Yeah, okay. The image, purple, is isomorphic to the domain blue over kernel brown. So that cancellation is an intuitive computation we did, but in order to prove that, in order to prove such crossing out is correct, I can really cross out Z2, Z2. Can I do that in general? Well, here's the justification. Get the epimorphism from Z4 times Z2 to Z4 with kernel 0 times Z2 so that we get the conclusion. Okay, it took enormous efforts to get the theoretical background done. Actually finding out this epimorphism phi, well, what about it? Stop the playback and try to get one. Turns out, it's right here. By the way, solution 1 is what we just discussed. Solution 2 here gives me the solution. Phi is actually the projection pi1. The projection to the first coordinate, disregarding the second coordinate y bar. So no matter what I have in y bar, it doesn't matter. As long as the first coordinate, x bar, is 0, this entire thing will go to 0. So the first coordinate has to be 0. First coordinate has to be 0. And indeed, the first coordinate has to be 0. So that's the kernel. And then the domain over kernel is the image. So we went through a computational problem with simple computation and then difficult justification. But what we want to do, of course, is just simple computation always works. We want to prove that. That may be a bit hard, but once you get through that, then we can do this all the time. And that's what we're going to do in section 6. Let's start from examples first. No, excuse me. We're going to do section 2 in a separate video. We don't have enough time after all. So let's stop here.